Okay. Chebychev's theorem is used when you don't know for sure if the distribution is skewed right or skewed left, or you don't really know what shape the distribution is. Then you can use Chebychev's theorem. It can be used for all distribution regardless of the shape. And it tells you, for example, if k is 2, that at least, put the 2 in here, you get 3/4, at least 3/4 of the data will fall within 2 standard deviations of the mean. So it's not real exact. Okay, it's at least. It's giving you a range, but not giving you a real exact number. Empirical rule is going to give you a better estimate. It can be used when the distribution is approximately normal or bell-shaped. This is what we mean by normal. Tallest bar is in the middle, kind of tails out both ways. Sometimes we call it bell-shaped because you kind of draw a line here. Kind of looks like a profile view of a bell, side view of a bell. Here's what it says. If you know the data is approximately normal or approximately bell-shaped, which a lot of real-life data is, heights, weights, test scores, pretty much all of that stuff is bell-shaped in the real world. If you go to the mean, say this is the mean, then you go 1 standard deviation to the right, 1s, and 1 standard deviation to the left, so minus 1s. 68% of the data is going to fall within 1 standard deviation of the mean. If you go 2 standard deviations from the mean, x bar plus 2s, x bar minus 2s, 95% of the data is going to fall in that ratio. And these are numbers you're going to have to know. These are not on your formula sheet. I don't want you to write them on there. I want you to memorize these 3 numbers, 68, 95, and the last one, if you're 3 standard deviations from the mean, so we're out here 1, 2, 3, x bar plus 3 standard deviations, 1, 2, 3, x bar minus 3 standard deviations, then 99.7% of the data is going to fall in there. Any questions so far about that? So let's take IQs as an example. The mean IQ is 100. The standard deviation of the IQ scale is 15. These are accurate. I'm not making them up. So let's say that we know IQs are normally distributed. Most of us are in the middle, average intelligence. You got a few people really low intelligence. You got a few people that are extremely bright. But the majority of us are all in the middle. Okay? Let's say somebody comes up to you and says, hey, I've got an IQ of 150. What does that mean? Well, IQ of 100 is the mean. So if we go out 15, so this would be 115, 130, 145 would be out here. 3 standard deviations above it. We go down 15, down another 15. So subtract 45. 55 would be 3 standard deviations below the mean. This is 99.7% of the data. So if someone's got a 150, are they smarter than most of us or not? Yeah. Well, they're pretty darn smart if they really have an IQ of 150. Either they're lying to you or they're extremely intelligent. Now, what percent of people in the world would have an IQ above 145? If I know 99.7% fall between 55 and 145. If I subtract that from 99.7 from 100, I get 0.3%. So 0.3% of people in the world are either IQ above 145 or an IQ below 55. So what could I do to that number to just get the percent that's above 145? Right, divide by 2. So 0.3 divided by 2, 0.15%. 0.15%. Or, move your decimal 2 to the left, 0.0015. That's 15 10,000s. So I have 10,000 people. So if I take Manchester plus another town that's the same size as Manchester, join them together, that's 10,000 people. There's only going to be about 15 of them that have an IQ above 145. In Manchester's, there's probably about 7 or 8 people. that have an IQ above 145.
Can you use that theorem to find out what the percentages are?
Well, see this theorem, you could. That's a good question, Jenny. Let's say we go out 3 standard deviations. We put a 3 in here, so we do k equal 3. So we get 1 minus 1 over 3 squared. That comes out to 1/9. So, or excuse me, 8/9. So this is going to tell me that at least 8/9 of the data will be in here. And 8/9 is about 88.9%. So Chebychev's theorem would tell me that at least 88.9% is in here. The empirical rule tells me it's almost exactly 99.7%. So the empirical rule gives you a lot more exact answers, because you know the data is bell-shaped. When you use this, you don't know that the data is bell-shaped. Okay, so empirical rule is better if to use because it gives you better answers. Okay, let's have you go ahead and try it, work on the rest of the assignment here. I'm going to give you about another 5 minutes to work, then we're going to head to the computer lab. 5 or 10 minutes, then we'll head to the computer lab. So, if you didn't pick all that up, empirical rule is right towards the end of section 3.3. It's got a nice explanation of it in the book too.